This conference will now be recorded.
So today we'll be discussing optoelectronic devices. So far in this chapter we had learned the main part is PN junction diode, right? PN junction diode. And we have studied various biasing like forward biasing, reverse biasing, and we have seen the IV characteristic upon applying external voltage, whether external electrical voltage. So in this optoelectronic devices, this section today we'll see how semiconductor diodes upon shining light can produce or generate electricity, and in other way also. So this is actually photodiode. We'll tell you that. So we'll learn about semiconductor diodes in which carriers are generated by photons. So charge carriers will be generated in these optoelectronic devices. What happens? Charge carriers are generated by photo excitation. Photo excitation. Okay, and those charge carriers will conduct in the device. So these devices are actually called optoelectronic device. That means if you shine a PN junction diode, then it will emit light one way, or if you shine with light, it will conduct, or in other way we'll see light emitting diodes are also there. So when you apply forward bias, then certain particular diodes will emit lights. Okay, so those are called light emitting diodes. So basically today we'll be discussing three different optoelectronic devices. One is photodiode, photodiodes, optoelectronic devices we'll be discussing: photodiodes, light emitting diodes, and photovoltaics. Photovoltaics. Photovoltaics, here what it converts photovoltaic, they are used to convert optical signal, or sorry, optical radiation into electricity, into electricity. Okay, so this is, see, photodiodes are used as photo detector, photo detector, light emitting diode, LED. You know, LEDs are widely used in the modern society. Okay, and this is actually solar cells, photo solar cells. Okay, so alternative power for the future. Okay, or future universe. Okay, so we'll first discuss about photo diode, then we'll one by one discuss this light emitting diode and photovoltaics with proper diagram, etc., and photo what are the IV characteristics. All those things we'll discuss here today. So first, let us discuss about photo diode. So photodiodes are actually special purpose or special made PN junction diode. I'll write few points. So these are actually special purpose, special purpose PN junction diode. Okay, and see here, PN junction diode is actually heavy. Both P and N sides are heavily doped diodes. Okay, heavily doped, heavily doped, heavily doped. Both N side and P sides are heavily doped, and this diode is operated. This photodiodes, they are operated in reverse bias. I'll tell you why reverse bias is mode of operation for photodiodes. Operated in reverse bias. And then discuss for that. And so these are the points. So special, this is a junction diode, special purpose PN junction diode. Both P and N sides are heavily doped. Okay. Now we'll see, try to understand the working principle of this diode. When a photodiode is illuminated, so construction is such that the depletion region or the junction is actually covered by transparent material such that light can fall on that junction. Okay, in the device. So in the device, this PN junction has to be covered with transparent medium. Okay, so that light can fall on the at this junction region. Okay, or the depletion region. So when such a diode is illuminated by photon or light having energy h nu, certain energy. Okay, if this energy is greater than the band gap, you know the band gap. I hope you remember. Band gap means in semiconductor material they have conduction band having energy EC. Then you have valence band having energy, okay, EV, and the gap between this conduction band and valence band is called band gap, and the energy corresponding to this gap is called band gap energy, that is denoted by Eg. Now when a photodiode is illuminated by a light of photon h nu having energy h nu, If the H nu energy is greater than the band gap energy, then what happens? There will be generation of electrons and hole pairs. Electron, E for electron and H for hole. Electron hole pairs will be created. Okay, so electron hole pairs will be generated, and the fabric this p-n junction diode is such that this electron hole pairs will be generated in this depletion region only. Why? Why in this depletion region, near the depletion region? Because there is a elect huge potential or electric field across the junction. This is due to built-in potential. Okay, due to built-in potential, you remember that, I hope. So there is a huge electric field across this junction. So this is the n side. N side has actually high high potential, and p side is low potential. That's why the electric field is directed from n to p. So this is n, this is p. N to p. Electric field is denoted, directed from n to p. Because of this large electric field, the electron hole pair generated at this junction, p-n junction, or near the depletion region, will be actually attracted by, like attracted or collected on either sides of this junction. Like see, holes are connected. See, holes will be going along with the along with the field direction. So if suppose electrons and holes are created at this depletion region, then what happens? The electrons filled dot and holes are empty dots. So holes will be collected by p region, and electrons will be collected by the n region. Okay, and thus this, see, holes are there and electrons are there all the way. So this charge separation will build electric potential. Okay, EMF. It will produce an EMF. So what happens when you shine a diode with light having energy H nu? If that energy is greater than the band gap energy of that particular semiconductor diode material, then electron and hole pairs will be created near the depletion region. And here there exists a huge electric potential. Due to that, the holes will be collected by p region or collected in the p region. Electrons will be collected in the n region, and this charge separation will produce a huge EMF. This will produce a EMF, like an EMF. This EMF, sorry, this EMF, this EMF. Now, if you connect to external devices, then you will get photocurrent. Okay, photocurrent, that is called photocurrent. You will get photocurrent. Okay, so if the electron holes pairs are not created in the depletion region, then there might be a risk, there might be a possibility of recombination again. Okay, that's why the electrons and holes must be created or produced in this depletion region or near the depletion region, such that the holes will be collected by p, okay, and electrons will be collected by n region. That will create an EMF. So positive, they will behave as positive charge, this will behave as negative charge. So if there is charge separation positive and negative, then there will be an EMF produced across the junction. Okay, so this EMF, if you have a battery, it has EMF, and if you connect that battery to external circuit, it will drive a current. Similarly, here if you shine with light and there is a flow of current in the external circuit. Okay. So this is the working principle. Now we'll see this IV characteristics. So as I said, photodiodes are operated in reverse bias. Okay, and that's why you can see the reverse bias. This is the saturation, reverse saturation current, and the magnitude of the current depends on the intensity of the photon, because intensity means what? Increase the intensity, number of individual photon will be increasing. Okay, number of individual photon will increase, and hence it will create more and more. If suppose there were 50 photons, then it can produce 50 electron hole pairs. But if you have 1000, then they can produce electron hole pairs thousands. Okay, so that's how intensity of the current will increase if you, sorry, of the current will increase if you increase the intensity of the light you have used to shine the diode. Okay, so that's why you can see I1, I2, I3 increasing order. See, you have this current increasing order and intensity also in the increasing order. Okay, now the question is why photodiodes are operated in reverse bias. In reverse bias, I'm writing in short reverse bias RB. Okay, look here, electron and hole pairs are generated in equal number, right? Suppose I take a n type. If I and take an n semiconductor n type semiconductor. Now I am discussing why these photodiodes are operated reverse bias. So let us take an n-type semiconductor, and in n-type semiconductor, majority charge carriers will be electrons. Majority will be electrons, right? Majority will be electrons, and minorities will be holes. Okay, minorities will be holes. Now look, if I take this p-n junction diode and shine a light on that, then what happens? The electron hole pair will be generated. That means if suppose earlier the concentration of P, which is a majority carrier charge carrier, is like if the P is the concentration of the charge carrier before okay, so before the generation of charge, then see delta P, suppose, so P prime, the concentration of the charge carriers now upon shining with light will increase because there will be change in the charge carrier, because electron and hole pairs will be generated. Because of that, there will be change in the charge carriers. Okay, total number of charge carriers. So this is delta n. This is the change in the electrons, and this is the change in the holes. Okay, this is how I denote now. Now look, in the forward bias, electrons goes from N to P, and holes are going from P to N. That means the majority carriers goes to minority region. Okay. Now in the reverse bias case, the current is dominated by. We can show that the current is dominated by minority carriers, charge carriers. We can show that even though there is a same number of generation of electrons and holes, but take the fractional change in the electrons, fractional change in the electrons, and fractional change in the holes. See, since this n is much greater than p, so this ratio, this fractional change in the charge carriers with respect to like fractional change of the electron will be much less than the fractional change uh, in the fractional change of charge carriers in the p region. Okay, or minority charge carrier, because majority charge carriers are electron, n is much greater than p. Okay, n for electron, p for hole here. I'm just supposing. Okay, now see that charge carrier density, fractional change in the charge carrier density of delta n by n, and fractional change in the holes will be delta p by p. Like fractional change in the charge carrier in the, yeah. So due to generation of hole will be delta p by p. Since this n is much greater than, because it is n type semiconductor, n is much greater than p, then this change delta n by delta p, because see delta n will be equal to delta p, because the change in like the electrons and holes will be generated in pair. Therefore the change in this concentration of electron and change in concentration of holes will be the same. This will be the same, but this ratio now depends on only this individual number, this n, or the concentration of electrons, and p, concentration of holes. So if I see delta n by n, this fraction is much less than delta p by p, because this p is very less quantity compared to this n. So when we see such a large change, such a large fractional change in the charge carrier in case of reverse bias condition, I'll clean everything. So when you see this change is much greater fractional change in the electron, then current current is dominated by current is dominated by minority charge carriers. Minority, I'm sorry, so current is dominated by minority charge carrier. Okay, minority charge carriers. So look, the fractional change in the minority charge carrier is more in the more than the majority charge carriers. Therefore, and also we know the current conducts in case of reverse bias by minority carriers only. Therefore, the photodiodes are operated in reverse bias condition such that a large change in the minority charge carrier can produce a produce an effective change in the current, effective change in the current, effective change in the current, and this change will be of greater amount or sufficient amount to detect. Okay, so that's why the photodiodes are operated in reverse bias condition. Deepa, do you have any doubt? Do you understand this statement whatever I have discussed now? Do you understand why uh, photodiode is operated in reverse bias condition? Because fractional change in the minority charge carriers will be more upon shining light, and in reverse bias condition minority charge carriers dominate, or they take part in carrying current. So if we operate this diode, photodiode, in reverse bias condition, because the fractional change in the minority charge carrier is more, you will see a greater change in the current, and greater change in the current will be effectively measured. Okay, and because of that, the photodiodes are used as detector where you can detect various colors of light, various intensity of light. Okay, so photodiodes are used for photo detector. Okay, and they are operated in reverse bias condition because large change in minority carrier will give rise to large change in the effective current only when we operate photodiodes in reverse bias condition. Okay, so this is very important. Why this question comes in board exam as well as various other exam, or fundamentally you should understand why photodiodes are connected in reverse bias condition or operated in reverse bias condition. Now we'll go to light emitting diode or LED. Okay, okay, so here the photodiodes, they have circuit symbol as this is the diode, and if you draw some arrows, so this means photo diodes, not only diodes, these are photodiodes. Okay, or photodiode here, a single one. Okay, this is photodiode, circuit symbol of photodiode. Okay, we'll so LED means light emitting diode. Okay, light emitting diode. So this LED or light emitting diodes are operated in forward bias condition. Okay, forward bias condition. What is the working principle in this case? What is the working principle for LED? It is exactly the opposite to photodiode. Okay, see, I have PN junction, this side P, this is N. It is always operated in forward bias condition. That means it is positive, this is negative. Okay, this is the depletion region. So what happens when we use or bias this PN junction diode in forward bias condition, then see holes will diffuse to this way, and electrons will diffuse in this way. Okay, electrons will come to this way. So in this due course, what happens? The one electron, okay, one electron and another hole, they recombine each other. So this is called recombination. Okay, recombine or recombination. Okay, so when an electron and hole they combine or recombine, then what happens? See, you have effectively positive charge, effectively negative charge. If they combine each other, what will happen? Upon combination, electron hole, their existence will be totally uh, so they will be totally disappeared, and in place of this electron and hole pair there will be emission of energy in terms of photon, emission of energy. Okay, so emission of energy in terms of photon. Just a minute, I'll just change the digital pen because it has little difficulties in sensitivity. So emission of energy, I'll change it, and just in a minute I'll change it. Yes, so I'm back. So there will be emission of energy upon recombination of holes and electrons in terms of photon, in terms of photon. Okay, in terms of photon. That's why this LED is called light emitting diode. So when you operate, is these diodes are also uh, very much useful modern life, because LEDs are nowadays used many places in our life. And see, in LED there can be various colors of LED. Okay, colors. So how do you get different colors of LED? So see, as I said, if you get a PN special diode, not all diodes are LED. Okay, not all diode can act as LED. Some diodes are there which will act as LED. But how do you? Okay, so how to determine will give you visible light? Actually, see, in in any case, there will be electron hole, electron and hole recombination will be there always. Okay, this happens always for any type of diode. But the problem is the energy generation of energy upon recombination will not come as photons. Sometimes if you just take simple silicon or germanium, in this case also recombination happens and the energy manifested as heat energy, manifest as heat energy and increase the temperature of the silicon or germanium diode. Okay, so it depends like which will act as LED and emit light in the visible range. So if you want to fabricate an LED, you have to keep some concept in mind that the band gap of the semiconductor material, band gap, this is very important, this term band gap. So band gap has to be within this range 1.8. Okay, so in between this range you have to have the band gap of the material you use to make LED or light. Why? Because if you use those materials having band gap around 3, this will actually produce the light which will be nearly 400 nanometer range. 400 nanometer, because we know the visible light has wavelength range 400 nanometer or 4000 angstrom to 7000 angstrom or 700 nanometer. Okay, in this range, if the frequency, sorry, wavelength of the radiation happens like the electromagnetic radiation with this range are called actually visible light. Now, a diode, junction diode, whether that will heat up the diode or that will emit visible light, that depends on the band gap you have for this diode. Okay, if the band gap varies between 3 electron volt to 1.8 electron volt, then so this 3 electron volt corresponds to 400 nanometer and 1.8 electron volt corresponds to 700 nanometer wavelength of the radiation emitted by LED. Okay, so this is how you have to consider the band gap, and that band gap actually the wavelength or the frequency of the light emitted purely depends on the band gap range. Okay, as I said, pure silicon or germanium would be an LED. So you can use this, but along with that, you have to use various other like silicon carbide or cadmium sulfide, etc., or here gallium arsenide, etc., gallium arsenide phosphide. Those materials are used in making LED. Now we'll see few advantages and uses of LED. So there are many advantages of our normal incandescent lamp, because LEDs are LED. So LED replaces, so uses of LED. LED replaces incandescent lamp. Okay, lamp, because incandescent lamp needs a high power or large power to operate, but LED needs very less power. So power consumption, to reduce the power consumption, people use LED. LED can be of various colors like red. Basically, red LEDs are used in many switches to see whether there is presence of electricity or not in various board. In see, yes. So LEDs are used in many places. Okay, all right. So we'll go to the last one, that is the solar cell or photovoltaics. So it has actually photovoltaics. It has working principle similar to photodiode. I'll discuss it once again. Photodiode. Okay. So what happens here? You look. You have a metallized finger electrodes. So these are the kind of finger electrodes. You have see there are slabs of N type material, P type material, and there is a backing contact, and in the back there is a metallic contact, and here there are metallized finger electrodes. This is the top surface. Top surface generally made very flat or having larger area such that it can collect more solar energy or photons. Okay, so there are three things happens here. One is generation gen- generation of charge carrier. Okay, generation of charge carrier, generation of, okay, let me write in. So three things or three aspects are important here in the solar cell. One is generation of charge carrier, of charge carrier, simply carriers. Okay, then separation of the charge carrier, separation of carriers, and third is the conductivity. Okay, conductivity. These are the few points about solar material. Like see, there should be generation of carriers very easily. A huge number of charge carriers should be generated. Okay, and those charge carriers will be separated by this huge electric field present there across the depletion region. So holes will be going this way. Okay, so this is called separation. Generation is due to, see, if you shine depletion region with or a diode with solar light, what will happen if the energy then band gap energy Eg, then there will be electrons and holes pair. Those will be separated by this electric field, which is naturally created across the depletion layer. Now those charge carriers, see, the electrons are collected by front electrodes, and back electrode is this one. Here holes are collected in the back electrode, and this is actually covered by this arrangement is covered by a transparent material such that photons can hit or can penetrate the material, okay, or fall on the material. So you can see here the electrons will be collected by this electrodes, top electrode and back electrode, or these are called, yes, top electrodes or front electrode, and back electrode will collect the holes, and there will be a, see, if it, if, see, this slab has a negative charge upward and positive charge downward, there is a charge separation, and due to that there will be EMF generated. And this EMF, like, see, a simple battery, if you have a simple battery, it has certain EMF. And now if we use this cell and connect to external circuit, then we will get electricity, okay. I hope you have understood. I'll just tell you briefly once again. when sign when a solar cell or photovoltaic cell is illuminated by solar light, what happens? If the energy is greater than band gap energy, then there will be electrons and holes pair generated. Those will be separated or collected into different electrodes, top and bottom electrodes, and therefore, see, in the top there will be electrons and in the bottom there will be holes, so positive. So when there is a charge separation between positive and negative charge, then there will be an EMF produced. That EMF will drive the current if you connect an external circuit to it, okay. So this is the working principle of solar cell. Now we'll see this graph. This is very, very important. You can see this IV characteristics here. This IV characteristics is very, very important. Look here, the IV, in the IV characteristics you can see only a curved line in the fourth quadrant, okay. Why in the fourth quadrant? Because the solar cell does not require any input, that's why it does not require either current or voltage input, that's why it is drawn in the fourth quadrant, okay. Solar cell does not require any input, only you need to shine the solar cell with solar radiation, and that will produce the EMF, okay. So look, this curve is important in the sense, maybe this curve will be given in the exam, and then you will be asked what is this value. This is open circuit voltage on the voltage axis. See, this point is called open circuit voltage. In the current axis, this is called short circuit current. This much is short circuit current, this much is open circuit voltage, okay. This terminology you should remember. This is open circuit voltage and this is called short circuit current, okay. All right, so here also materials, like all the materials cannot give you proper efficiency because the carrier generation, so this also works in forward bias condition, but the opposite direction. So that's why it is acting as like acting similar to a battery or cell. In the battery or the current flows inside the battery in the opposite direction. So here in this case, solar cell is connected or operated in forward bias, but current flows in reverse direction, okay. And here also, by tuning the band gap, the efficiency or the amount of charge carrier generation is being tried to increase and such that you get more power out of solar cell, okay. So still in this modern age also, the solar cell research is going on in wide range to improve the efficiency or to how to improve the generation of power using solar cell. Basically, solar cells are used in series, not a single solar cell is used in the solar panel. You can see there are actually many cells connected in series such that you get a considerably large amount of EMF across the electrodes. Okay, so yeah, so this is how various electronic devices, basically these optoelectronic devices are very important, and we have discussed how they work, what are the working principle, and what are the IV characteristics mostly, and what are the significance of those uh, IV characteristics that we have learned, and what else we have learned. We have learned in which bias they work and why. So those things are discussed in today's class. So today we'll stop it here. Next day we'll start with transistor. Transistor is another important and very interesting topic which will start on Sunday evening. Okay. Okay. So bye for today. Deepa, if you have any doubt, you can ask me some quick doubts, or maybe you can ask doubts in the next class. So shall we end the class here now? Okay, so we'll discuss your doubts on Sunday before Easter. Today we'll stop it here. Okay. Okay, bye for today.